In the last group of lessons, we noticed that some places on Earth have lots of mineral resources and others have few. When we look closely, we start noticing patterns. That's when it's time to kick in our ability to think and act like a scientist. Whenever we observe a pattern, we wonder, what caused this pattern? Then we gather evidence and develop and support a claim that will answer that question. This is a pretty common way that scientists put together the cross-cutting concepts and practices from the NGSS. We begin lesson 1.7 by discussing why do scientists ask questions, and we realize that helps them focus their investigation. Once they get an answer to that question, we call it their claim. But how do we convince people that our explanation, our claim, is actually correct? The interactive presentation goes through this with a sample mystery, a scenario involving where the other half of Half Dome went. Students will go through and ask a question, make a claim, collect evidence, and use that evidence to support the claim, and provide reasoning connecting the evidence to the original claim. Students then examine a rubric that highlights the criteria for strong claims, evidence, and reasoning. The phenomenon that we want to explain in this group of lessons is that Earth's material resources are unevenly distributed. We begin lesson 1.8 by revisiting the unit roadmap and the map of unevenly distributed mineral resources. Once students have asked the question of what causes this distribution, it's time to jump into a possible explanation with a skit. Students act out a discussion between the scientist Alfred Wegener and some of his peers in the early 1900s. Wegener proposed a reason for this uneven distribution of resources, that the continents were constantly moving. Like the scientists of the day, we want our students to ask, what was Wegener's evidence? Students analyze the data themselves by trying to put together the continental puzzle to see if the continents really might have moved around and fit together at some point in the past. In lesson 1.9, students complete their continental puzzle activity, matching rock and fossil types to provide evidence that the continents used to be in different places than they are today. A worksheet scaffolds them through creating claim evidence reasoning paragraphs, modeling what Alfred Wegener did with his peers. Students learn then that Wegener's peers were not convinced that the continents were moving because they wanted to know about the processes that caused the continents to move. Students answer an exit ticket asking how they feel about the scientists being skeptical of Wegener's theory. We end the lesson with our first unit concept checkpoint. These are challenging conceptual questions that we discuss as a group to see if students have really retained and if they can apply some of their key discoveries so far in the unit. In lesson 1.10, students review yesterday's exit ticket. What additional evidence could we add? We ask the students, how would moving continents affect the seafloor? We use this question to transition to looking at several data sets showing the shape and the age of the seafloor that scientists have collected in the decades after Wegener died. Students participate in an interactive presentation highlighting the data from these new technologies. Students analyze images to identify mountain chains along the middle of the ocean, and they wonder, how could mountains form in the middle of the ocean? When they look at the age of the rocks on the seafloor, they find that these mountains are made from the youngest rocks in the entire ocean. In fact, new magma erupts at the very center of these mountains. This is evidence that the two halves of the ocean are spreading apart from one another, and magma is essentially leaking upwards to fill the gaps. Students build paper models of this process to make sense of the age and seafloor shape data. In lesson 1.11, students use their models to construct explanations of the mechanism of seafloor spreading. They then watch a video that summarizes the process in a different way, and they have the opportunity to revise their explanations. Finally, students write claims, evidence, reasoning statements that answers the question, how does seafloor spreading support Wegener's idea of moving continents? Lesson 1.12 addresses the question, how do we collect seafloor data? Professional scientists use sonar to map out the seafloor. Students will simulate this experience using the built-in rangefinder on their Pocket Lab devices. They make paper models of the seafloor mountains and then collect rangefinder data using the Pocket Lab. How well does their data match the shape of their model seafloor? They then return to the real seafloor data to discuss how it was made using a rangefinder located on the bottom of a ship. Lesson 1.13 helps students address the question, how do plate movements relate to smartphone materials? The teacher leads students through a discussion about how plates can move mineral resources around. Students won't have all the pieces yet because they don't know about all the ways minerals form. That comes in the next group of lessons. But they should be able to start putting together what they do know. They demonstrate that by creating epilogues of the original skit from lesson 1.8 to vindicate Alfred Wegener. They present these skits as summative assessments of their understanding of how plates move around and are evidence that that actually happens. We provide a rubric to help you score the skits. Students are starting to be able to explain the patterns they see in the mineral resource distribution. They'll be able to say more once they learn more about how rocks and minerals form. And that's up next, the rock cycle.